The topics we're going to talk about today are balances on reactive processes. We're going to kind of continue that. We're going to talk a little bit about stoichiometry. We're going to particularly focus on combustion reactions, which basically involves single phase systems being a gas. And since we're talking about gases, we're going to be dealing with ideal gases and ideal gas mixtures, particularly combustors, so CH4, methane, that kind of thing. Talking about what's been worked on before, I want to kind of talk a little bit about wolframite, just because on the week 6 problem set, there were some balance equation problems that you had to do where you were dealing with wolframite. And wolframite is it's a mineral series, so it's iron, manganese, tungstate, and so either iron or manganese bonds with the WO4 molecule to form this mineral. And the iron and the manganese also both have the same oxidation state, basically. And other mineral series, we tend to call this a spinel if you have a mineral series. And the spinel, it's kind of a good example, is a so-called magnesium spinel. And these four metals can bond with Al2O4, basically. And so this flavor of aluminum oxide. So you can have magnesium, iron, zinc, or manganese. And so spinel is just a magnesium spinel. Gahite is a zinc spinel where the zinc bonds with Al2O4. Herkinite, it's an iron spinel, and FeAl2O4, so iron aluminum oxide, and galaxite, which is kind of a cool name, manganese spinel. So we come across these mineral series. I threw in the wolframite because tungsten's kind of one of my favorite metals. It was the filament material for light bulbs, basically. And I kind of have this anecdote how I had a friend who went and interviewed with Sylvania Light Bulb, and that was obviously a light bulb company for Sylvania Light Bulb. And midway through the interview, he stopped his interviewer and asked, because he had a bunch of documents, I suppose, and asked what W was. W is, of course, the symbol for tungsten. The Old English word for tungsten is wolfram, and wolframite was actually mineral that people that in the early days, I guess the Bronze Age, who were smelting tin, had problems smelting tin ore if it had wolframite in it. And they supposedly said, well, it would devour our tin like a wolf. And so that's how wolframite gets its name, and how the element tungsten has its elemental symbol W for wolfram. Some kind of trivia there. Kind of more tidbits on tungsten, so it's very interesting. The specific gravity of tungsten is 19.3. The specific gravity of gold, or arum, which is why it's AU, is also 19.3. So there's a potential for counterfeit. And if you're doing specific gravity measurements of gold, you have to have very, very precise instrumentation, probably the second or third decimal point to really tell the difference. And you can look around YouTube. There is an alarm, actually, that a great amount of the world's gold supply, particularly in the financial sector, is actually tungsten bars that have been coated with gold and passed off as the real thing. And so that's another little tidbit of tungsten. Another tidbit of spinels, titanate spinels. So this was kind of a real world problem I dealt with at one point in time. And we were making dielectric materials. So barium titanate and strontium titanate are both very good insulators. They have a very, very high dielectric constant. And we were making basically insulator-based antennas. It was kind of cool. And we were dealing with strontium titanate, and it's all part of the spinel series, this titanate spinel series. And calcium titanate is not very good for dielectric applications, or at least the applications we were caring about. We wanted pure strontium titanate, so we purchased some pure strontium titanate. We're not getting the properties we wanted, and put it in the old XRD. So this is diffraction spectra from an XRD, and found that our our material was strontium calcium titanate, basically. They called it titanium oxide. Um, so there's some purity issues, and so separating spinel series out into individual mineral spinels like we have here is actually kind of difficult because the oxidation state of all the attaching elements is the same. Anyway, now we're going to talk about ideal gas stuff. I don't know, I probably should have put something a little more technical, but the ideal gas law, if you will. PV equals nRT. P is pressure, V is volume, N is the number of moles, and T is temperature. And we have different flavors of the ideal gas constant. And a lot of times in this course, we will use PV equals nRT a little bit later. We'll use this flavor of the ideal gas law, P1 V1 over T1 equals P2 V2 over T2, to kind of calculate volumes and pressures at different conditions. We'll use this flavor a little bit more. And these ideal gas constants are pretty important. When we talk about energy balances, we really use this one quite a bit, the 8.314 joules per mole Kelvin. The one we use a lot of times for gas is 0.0821 liters ATM gram moles Kelvin per gram moles Kelvin. And Kelvin is the scale we use here, and we'll see a little bit more in a little bit later. Excuse me. The ideal gas law is also important because it gives us the so-called standard molar volumes, and standard molar volumes are very, very helpful in solving solving problems if we are asked in terms of moles and that kind of thing. And STP 273 degrees Kelvin, 1 ATM. 1 ATM is also 760 millimeters of mercury, which is another flavor of a pressure measurement. Standard molar volumes basically tells us that there's 22.41 liters of an ideal gas per gram mole, or 22.41 cubic meters of an ideal gas per kilogram mole, or 0.0224 cubic meters of an ideal gas in 1 gram mole. 1 gram mole corresponds to that. When we're dealing with standard molar volumes, terminology such as 1 standard cubic meter basically means that it's an ideal gas at standard temperature and pressure. And so these conversion factors come in handy in some of these combustion problems that we're going to be working out. Partial pressures, so this is Dalton, and we've seen variants of are part of the way you figure out partial pressure already. So the total pressure is the sum of all the constituents in a gas, and the partial pressure, so P sub I is the partial pressure, so P sub T is total pressure. So P sub T, the total pressure, is the sum of all the partial pressures. You can figure out the partial pressure of an individual gas by multiplying the mole fraction of your individual gas in your gas mixture times your total pressure, or you can figure out the partial pressure by multiplying the volume fraction by your total pressure. And this here is kind of a proof that tells us that mole fraction is equal to volume fraction for an ideal gas. Okay, so if I tell you I have a gas mixture that's 50-50 by volume hydrogen and oxygen, it's also 50-50 by mole hydrogen and oxygen if it's an ideal gas. And so that's kind of important. It helps out with the solving of these problems. And this is kind of the proof, right? If PI equals YIPT and PI equals VIPT, we can set YIPT to VIPT and cancel the total pressures. So YI equals VI. Kind of a proof. I said it verbally. We could work it out if you wanted to. Anywho, if you wanted to know the mixture of a gas mixture sorry, if you wanted to know the composition of the gas mixture, you only need to know the individual volumes. You can figure out the volume fraction, and we've done that kind of already. So volume fraction becomes very important because with volume fraction, you can directly interpret molar fraction, and you can also calculate partial pressure. So it's really kind of a useful tool. Here's an example of a combustion problem that we're going to work through here shortly. And you're running a plant which sources natural gas from both Canada and Tunisia. The gas from Canada contains 99.6% methane and 0.4% N2 or nitrogen, while the gas from Tunisia contains 70% methane, 15% hexane C2H6, 10% octane C3H8, 3.5% pentane C4H10, and 9% nitrogen, or 0.9% nitrogen, excuse me. What volume of air would it take to fully combust 1 standard cubic meter of each gas? And for this class, I don't know if you've done this in other classes, but for this class, we're assuming air is 21% oxygen and 71% nitrogen. So let's go ahead and work through this problem on a whiteboard, shall we? Great, everybody. We're still working with reactive material balances. And sorry, it's taking me so long to write. And there's kind of some things that we want to talk about. We talked about this a little bit before, at least in the lecture notes, and the whole kind of concept of gravimetric factor. And I've said this explicitly, well, maybe not explicitly. I've not said it explicitly, but we've used it. And we've had a problem before where we look at hematite. And that's Fe2O3. And so the gravimetric factor of iron in hematite is effectively 2. And if we see something like we have, 9,000 kilograms of hematite, and we can put it in terms of a mass flow rate. So 9,000 kilograms of hematite in 1 hour. How much iron flows in 1 hour? Or how many kilograms of this pure iron flows? Right, so this is kind of an example problem. It's loosely related to one you've seen before, and so the way you would start that out, and so a large part of this class is conversion factors. So we have 9,000 kilograms of Fe2O3. The question's asking how many kilograms of iron flows in an hour. Okay, so we want to know kilograms. No. So we're going to have to do some conversions, right? Because this gravimetric factor is molar. And I think maybe right now you're saying, hey, wait, we're talking about a combustion problem. Well, I'm kind of leading in to how we go about solving these combustion problems, working with a substance we've worked with already. so I'm not gone 100% crazy. So we start off with 9,000 kilograms of Fe2O3. And sorry if my railroad track got a little messy. We can do things in terms of kilogram moles. So we can say 1 kilogram of Fe, and we can just put in the atomic mass in terms of, or molecular mass in terms of kilograms. So it's 159.69 according to PubChem. And we had to introduce our molar relationship because it's a 2-to-1 ratio, basically, right? So for every 1 mole of Fe2O3, or 1 kilogram mole of Fe2O3, there's 2 kilogram moles of iron. So 1 kilogram, there are 2 moles of iron. And so this here is our gravimetric factor. And we've used it, but we've never really just said what it was. And so I noticed I had put it in some notes and figured I should kind of explain it a little more. So we have our molar ratio. So now we need to know the molecular mass or atomic mass of iron, and that's 55.85. So 1 kilogram mole of iron is 55.85 kilograms of iron. And usually I start at the top, but I was doing it because I was mentally canceling already. And so I don't want to confuse people by the way I write stuff down. But at the end of the day, after the railroad track is written, always go back and inspect the units. Always, always, always. And always look at them to make sense, right? Don't just line them up so they cancel. Actually make sure it makes sense. And that kind of comes into play with some other cancellations. So kilograms hematite cancels. Kilogram moles Fe2O3 or hematite also cancels. Kilogram moles of iron now cancels. And we're going to get what we wanted. We wanted to know how many kilograms of iron flow in an hour. And forgive me if I'm somewhat grammatically incorrect. And so we have 9,000 divided by, that's a big mistake. So divided by 159.69, multiplied by 2, and multiplied by 55.85. And I got 6295, and always work these out along with me. And if you think I've made a mistake, shoot me an email. And I'll keep blue. Oh, and you know what I forgot was an hour. How many flows in an hour, and I forgot to leave that time there. So don't forget the units. I made a mistake. I apologize. But I am human. All right, so we used the gravimetric factor to figure that out. Now we're using the gravimetric factor in a global chemical equation. And we will take a look at this right now. And let me put the question that we said we were going to work out. And we're going to work out the easier one because we have the harder one in the week 7 notes. And let me kind of scoochy this guy over. And there we go. And hopefully you can read it. It pasted it in this fancy font, I guess. I should have pasted it as a picture. But you're running a plant, and we've read this already, which sources natural gas from Canada and Tunisia. The gas from Canada is 99.6% methane and 0.4% N2. And the gas from Tunisia contains 70% CH4 and these other stuff. And we want to know what volume of air would it take to fully combust 1 standard cubic meter of each gas. And we want to assume air is 21% oxygen and 79% nitrogen. And so, oops, I tried to switch pens. 1 standard cubic meter is kind of a key here. So we know we're at STP. And there's multiple ways to solve this problem. And I'll show them both to you. And sorry, I'm logged out of another item here. So we want to know what volume of air would it take to fully combust 1 standard cubic meter. And so we're going to use the Canada gas. And in the homework, you have to do, not homework, I problem sets. So week 7 problem sets. You have to do the Tunisian gas. Okay, so I'll do the Canada gas to kind of show you how it works. And so this is 99.6% CH4 and 0.4% N2. And in some problems we're asked like how much N2 is coming out the other side and that kind of thing. But this particular problem, we only want to know what volume of air. And this is kind of a key thing too. Air is what two components are air. So it's N2 and O2, and we're even told the composition. So air is 21% oxygen and 79% nitrogen. All right. And I'm going to just also assume STP. They're not given any temperature conditions or anything like that. And this is by volume. All right. So we're going to work it out kind of the long way. And I'm going to show that to you first. And I'll also show you the short way. And I'll highlight this so we know it's the long way. And the long way is work in terms of gram moles. And sometimes I only show the long way, but today I'll show the short way as well. So we know our composition, and we want to go ahead and work in terms of gram moles. And we have we want to burn 1 standard cubic meter of each gas. And so let's convert this to moles. So 1 cubic meter of gas, and standard actually does tell us it's STP, so we don't really even have to assume because it's kind of telling us. We can use our standard molar volume. And so 1 kilogram mole is equal to 22.4 cubic meters of gas. And let's go ahead and work in, we said we were going to work it in terms of gram moles. So I could have used the other conversion, and I didn't, but I've already written this one down, so we'll stick with it. 1,000 gram moles in 1 kilogram mole. And so this equals 44.62 gram moles of gas. And the gas is CH4 plus N2. Okay, so the whole volume of this gas is 44.62 gram moles now, and I'll write it in a different color. So now we know it's 44.62 G moles. Okay. And all right. So the next thing we need to know is what our reaction looks like. And so we need a balanced equation. And so our combustor, we can kind of write it this way. We probably want to write this somewhere. So we need a balanced equation. CH4 plus N2 plus O2 plus N2 yields. So this is, just going to break it down. And in the future, we kind of don't explicitly write this out if you don't want to, but for now, I'm going to write it out. Gas, air, and I'm going to put nat, so we know what we're doing. So this is our combustor. You could also label it combustor. Yields. Let me stick with the same. Oh, sorry about that. I don't know if that was much better. All right, plus N2. And I kind of have it written in terms of with N2, but N2 just comes in and out. And the problem's not even asking for how much N2 we're dealing with here. And so I'm just going to rewrite it without the nitrogen. So we know that nitrogen's not going to react. And even though I know in the next problem I'm going to say it's another way to look at it, assume N2 doesn't react. You really don't assume N2 reacts. It never reacts. Okay, so we know it's going in and it's coming out. We could even figure out the volume if we were asked. And we'll start incorporating that in kind of later problems. But right now, we don't care about N2 here. And I hesitate to write this because we kind of do care about N2 later when we're figuring out air. But we can figure out the amount of total air, but just the amount of volume, because we know the composition of air is a combination of O2 and N2. So I'm going to put something like sort of. And I'll highlight it in a different color. Sort of. Okay, so we don't care about N2 for this problem, sort of. And then we'll get to it. But for the balanced equation, we definitely aren't worried too much about it. So CH4 plus O2 yields CO2 plus H2O. And we can go ahead and do a balance. And I'm going to kind of use different colors for the coefficients to make it easier. Hopefully you can read it. And try not to use letters that overlap with the elements and that kind of thing. So our carbon balance, I'll do the balance in terms of blue. Let me see, X equals A. The hydrogen balance, for X equals 2B. And can already reduce this a little bit. Oops. Tried to write the number 2 and I could not. And for the oxygen balance, 2y equals 2a plus b, and just kind of rewriting that. So I probably could assume some things here. So I'm going to do things a little different than I usually do. I'm going to use a basis, and so if we have 44.62 gram moles of gas, instead of assuming a basis like we've done in the past, I'm going to plug in a basis. So plug in a basis. So we're going to plug it in. So how much CH4 do we have? Well, we have 44.62 gram moles of mass, 99 gram moles of gas. The volumetric ratio is equal to the molar ratio. So moles of CH4 0.996, which was the volumetric ratio. But for ideal gases, the volumetric ratio equals molar ratio. So 0.996 times, we had a total amount 44.62. Oops, messed that one up. Gosh, sorry. So 44.44 made a boo-boo. So 44.44 moles of CH4. So X equals 44.44. A equals 44.44. 2 times X equals B. So 2 times 44.44 equals B. So B equals 88.88. And kind of made this overcomplicated for Y, but we'll roll with it. I think I did anyway. 1/2 2 times, yeah, I think I did, but it'll work out. If I can write it, it'll work out. So yeah, I don't even know. Okay, anyway, it'll work out. So y also equals, right? And keep in mind, this is the long way to kind of do this problem. So there's kind of something we've done, right? We didn't really fully balance the equation. We used the equations that we would use to balance the equation to solve our problem, basically. And so we know now that Y is what? Y corresponds to oxygen, right? So Y is number of gram moles of O2, okay? And so now we know we have 88.88 gram moles of O2. So let's convert that back to volume, and I'll use the right conversion factor, or not the right conversion factor, but the simpler conversion factor, because we were given the three kind of conversion factors for standard molar volume. So we have 88.88 gram moles writing it out a little bit more, but that's okay. I think it's good for explanation purposes. And we have 0.0224 cubic meters in a gram mole for an ideal gas. And so that equals to 1.99 meters cubed of O2. And air is 21% oxygen by volume. So we can figure out, we can say this, so total air equals 0.21 well, we can make an equation for total air. Hold on. Let me go back to what I was really trying to write. To find total air, all right, so 0.21 times total air, because this is the percent of the oxygen, equals percent O2, really. So you can basically find total air by saying 0.21 times total air, and I'm going to say X for total air, equals 1.99, where X equals total air. And I probably should have written this first, so I didn't mean to make it more confusing. So X equals 1.99 divided by 0.21, and I'm going to leave the units, where X is total air. And if I work it out, I get 9.48 cubic meters. All right, so that's the amount of air it would take to combust 1 standard cubic meter. And so if you work out the Tunisian one, you can use 4 reaction balances to figure out the total air needed. So you need to figure out the amount of air. I'll give you a little hint. You need to figure out the amount of air to combust the amount of CH4, C2H6, and C3H8, and also C4H10. So the methane, hexane, octane, and pentane. You need to figure that out. There's kind of a shorter way to do this. Okay, and I actually don't usually have students do this, but I'll show it to you anyway. The short way and it's not that much shorter. All right, so now let's take a look at the short way. And the short way, we would use our balanced equation. We've already said that a volumetric ratio equals molar ratio, or else we couldn't have done it the long way. And so we're going to do things just in terms of volume, instead of converting to moles or gram moles. And so we need the balanced equation here, and so we can assume the basis. So we can say x equals 1, a equals 1. If x equals a, that makes sense. 2x equals b, so 2 times 1 equals b, so b equals 2, and y would also equal to 2. And so x is 1, y is 2, a is 1, and b is 2. So we can rewrite this. CH4, again, the balanced equation is the key. And so we have a 2 here and a 2 here. And so we had 1 cubic meter, so we're not converting to moles. Here we can insert our basis and use this as to kind of figure out the ratio. So how much CH4 is your basis? Kind of how it was up here too, actually, right? So the basis was here, was how much CH4 you had. This was the basis back here. But we're doing it the short way, so we're not converting it to moles. And the purpose of converting it to moles is to have students practice using the standard molar volume conversion, which is a very important conversion. It comes back again in thermodynamics and maybe other classes as well, but I know for sure thermodynamics. So how much CH4 you have is the basis. So we know it was 99.6% CH4. And this is one time where we kind of deviate from the 2 decimal point thing that we kind of agreed upon, because you really need 3 decimal points in this calculation. So pay attention to that as well, because you might get things off. So we have 1 cubic meter of gas and times 0.996 equals the cubic meters of CH4. And so 1 times, well, it's 0.996. Sorry, I'm laughing at myself. So it's 0.996 cubic meters CH4. And so now we know that we have 0.996 cubic meters. And here the gravimetric factor thing becomes a little bit more apparent, okay, because the molar ratio is the same as the volume ratio. So 1 cubic meter of CH4 gives us 2 cubic meters of O2, and that equals, it should be 1.99, so let me just work it out to make sure. All right. So 1.99, so I'll leave it, it's 1.992, but I'll leave it in the 2 decimal point thing. So again, we went through the whole equation balance, but now we know how much cubic meters of O2. And again, we want to know, and I'll keep it 1.99. Anyway, 1.99 cubic meters of O2. So, so we can do the same equation again, 0.21 times x equals 1.99 meters cubed. Oh, we can leave the units off. Where x is equal to total air, and again x, it's going to be the same because that's what we figured out up here. So 9.48 cubic meters. And again, usually I don't show people this because we're trying to get you to practice using this standard molar volume. And it's good to convert different ways. And also, there's always more than one way to do things. All right, we've worked out this problem. Let's go and work out another problem. And I'm kind of saying it's another way to handle combustion. We're assuming nitrogen does not react. And I shouldn't really say it's another way because we really assumed that nitrogen didn't react when we did all these balances. But one thing that we did, so I did the easy one, the harder one, it's in the week 7 problem set. So please work it out. Take the time, work through it, look at it. It helps to practice. Here we have 2 gases. So we have hydrogen and methane. Excuse me. So hydrogen H2, methane is of course CH4, 55%, 35% methane, and 10% nitrogen. We have a lot of conditions that we are seeing here. And so we have the nitrogen that's being fed to a furnace. The feed rate of the gas is 1,000 cubic meters per hour. It's fed at a pressure of 900 millimeters of mercury, a temperature of 100 degrees C. And the air, there's also some air being pumped in. It's dry, and it's actually fed at a pressure of 894 millimeters of mercury and a temperature of 1,000 degrees C. Okay, and then we have some exhaust leaving the furnace at a temperature of 2,000 degrees C and a pressure of 755 millimeters of mercury. And this is kind of part of a problem. And it's only asking what volume of air is required to combust this gas theoretically. It's STP, so that's kind of a big deal. And so here's the total reaction. So CH4 plus 2H2 plus 3O2 yields CO2 and H2O. One thing to note, when you start using other hydrocarbons, you need more oxygen really to combust everything. So that's why you want as close to CH4 as possible. When you're combusting this stuff, just kind of some food for thought. And here, so if you have multiple gas types, you can break down the reactions into multiple reactions. So here we've broken it down into 2 reactions. So CH4 plus 2O2, which is coming a reaction, hopefully you end up memorizing, yields CO2 plus 2H2O. And the second one for hydrogen, 2H2 plus O2 yields 2H2O. So let's work this one out on the whiteboard, shall we? All right, here's our other example. I pasted it as a picture. I don't even know if pasted is a real word, but I pasted it as a picture instead of text so I could keep the formatting, which is why it looks a little bit nicer than the one we did before. And I just cut it out, took it out of the slides, so the grammar is a little incorrect, but we have a gas containing 55% hydrogen and 35% methane and 10% nitrogen. We're feeding it to a furnace, and the feed rate of the gas is 1,000 cubic meters per hour. OMG, 1,000 cubic meters per hour. That's kind of a lot. The gas is fed at a pressure of 900 millimeters of mercury. And I said before, standard pressure in millimeters of mercury is 760 millimeters of mercury, I believe. I might want to look it up before I start telling people that, but I'm pretty sure it is. A temperature of 100 degrees centigrade, and That's another kind of important thing to note. We're in centigrade, and STP is in Kelvin generally for these calculations anyway. I tend to do it in terms of Kelvin, and so we'll work it out. We'll work it out this way, and I think it's more correct anyway. Even though here we won't deal explicitly with the ideal gas constant, we will convert to Kelvin, and I think I am getting hung up on it before I even read the question. The air is dry and it's fed at a pressure of 894 millimeters of mercury and a temperature of 1,000 degrees C, and the exhaust leaves the furnace at a temperature of 2,000 degrees C and a pressure of 755 millimeters of mercury. And the question asks, so here's what the question's very much asking. What volume of air is required to combust this gas theoretically at STP? And so we know STP has to come into play. And there's also something kind of interesting here. It only wants it at STP, right? And so we got all this other information. So we actually have peripheral information that we don't really need to solve this problem. And so if it's only asking what air is required to combust this gas at STP, the only thing we need to do is figure out how much gas is coming in. And then we figure out how much it would take to combust it theoretically. The amount of air for this problem, okay, so there's other problems where it'll matter. But I'm going to kind of use blue to kind of show the stuff that doesn't matter. The air is dry and fed, blah, blah, blah. This doesn't matter. And who cares? We don't know. We don't care for this problem. Okay, for other problems, we will probably care. But for this problem, we do not care because it only wants to know how much stuff or how much air is required to combust this gas theoretically at STP. And I'm going to kind of color code it. Not needed for this problem. And I don't know why my pen's writing so messy right now. That's very strange. So hopefully it's not too big of a nuisance. All right, so a little bit extra information we got. So the information that we do care about is the gas composition. And I'm sorry it's writing so sloppy. So we have, oh, this is very strange. It's writing without me even touching it. So sorry about that, having some sort of technical difficulty. That's kind of strange. All right, so I think I got over my technical difficulty. Yes. So gas composition, so we know we're 55% hydrogen, and hydrogen exists diatomically unless it's specified as monatomic hydrogen. So 55% hydrogen, 35% CH4, our good friend methane, and it's 10% N2. And we want to know at STP, so we need to know our conditions. And if we were caring about the air, the conditions of the air, and we were caring about the exhaust, we'd write all this other stuff out as well. But right now we're only caring about the input air. And later on, we will care about the output, the input combustion gas. Later on, we'll care about the exhaust, and we'll compare about the temperature and everything of the input air. Conditions of combustion gas. So the pressure is 900 millimeters of mercury. The temperature is 100 degrees C. And I'm going to go ahead and just convert it to Kelvin. And it's 373, because it's 273 degrees Kelvin is 1 degree Celsius, right? So 373 Kelvin, or you add 273 to Celsius to get Kelvin. That was bad, and I've recorded it. No shame. Okay, and volume is 1,000 cubic meters. Cubic meters. All right, so what are we going to know? We need to know the volume at STP of the gas, because they want to know what volume of air, what volume of air is required to combust the gas, theoretically, at STP. So since they want to know this, we need to figure out the gas at STP. So figure out volume of gas. All right, so the way we do that is our old friend P1V1 over T1 equals P2V2 over T2. And here, condition 2 is STP. So we can rewrite this as V2 equals P1V1 stupid taskbar is coming up. P1V1 P2 over T1 P2. And so this equals, so P1 is 900 millimeters of mercury. V1 is 1,000 cubic meters. And I try to use the railroad track always. P2 is PSTP, so that's 273 Kelvin. T1 is 373 Kelvin. And P2 is 760 millimeters of mercury. All right, so will our units cancel? Will we get what we want? So millimeters of mercury, Kelvin, and we're going to get cubic meters. And let me use, and I shouldn't cancel out the numbers. I canceled out the numbers. I should have been canceling out the units. But so 900 divided by 373 multiplied by 1,000 divided by 760 multiplied by 273, and I got 866.73. Oops. I'm gonna put of gas at STP. And we're splitting the reaction. And so we've split the reaction. So this is our total reaction. And so we can split it into two. And we can call this one reaction 1. And we can call this one 2. And in much the same way is, and again, we're looking for volume of air, so we're going to have to convert O2 to total air using our handy dandy conversion that we did on the previous problem. So I'll just go ahead and rewrite it as reaction 1, reaction 2. So reaction 1 is CH4 plus 2O2 yields CO2 plus 2H2O. And so our O2 volume, and all right, this is going to end up being like a memorized reaction, I think. And so how much CH4 did we have in our incoming gas? Let me check. We had 35%. So the gas was, if we go back and look, it was 35% CH4. And our total gas was 866.73. So 866.73 cubic meters of CH. What am I doing? I already wrote the H. CH4 and there are no, man alive, totally screwed this up. .73 cubic meters of gas, and there's 0.35 cubic meters of CH4 per 1 cubic meter of gas. And we can use our volumetric ratio again that we used previously on the so-called short way. So for 1 cubic meter of CH4, we have 2 cubic meters of O2. Okay, and this is again the so-called gravimetric factor, and we kind of see it twice really here. And then what are we going to get? So will our units cancel? So cubic meters of gas cancels, cubic meters of CH4 cancels, and now we have cubic meters of O2 as our remaining units. And so 866.73 times 0.35 times 2, and 606.71 cubic meters of O2, and this is from reaction 1. From reaction 1. So reaction 2 was H2. So hydrogen, H2 plus O2. There's no CO2 in this one. So it just yields good old-fashioned, good high quality H2O. And I need to balance this. Two and two. All right. So again, we have our same basis, 866.73 cubic meters of gas. We know that it was 55% H2 from this here, and also the problem, 55% hydrogen. So same kind of concept here. .55 H2, 1 cubic meter of gas. And we have a different ratio now. So we have 1 cubic meter of O2, because this is understood to be 1, and I don't want to write it because it looks like a 10, over 2. Alright, so let's see, will the units cancel? Cubic meters of gas, cubic meters of H2. It's going to be a much smaller amount. 866.73 times 1.55, and then divided by 2. And I got 238.35. Cubic meters of O2 from reaction 2. And so total O2, and we'll see this over and over again in the course, where we figure out individual components and just add them all up. And that's kind of a common repeating theme. So it equals 606.71, and this is from reaction 1. Plus 238.35 cubic meters, and this is from reaction 2. And that is equal to 800. Oops, what are you doing, machine? Just went off. Let me plug and chug here. 0.71 plus 238.35. I got 845.06. And it was asking for air. So we can we'll do our equation again. So 0.21 times x equals 845.06 meters cubed, where x is total air. Or we could say total air equals 845.06, that's horribly written, over 0.21 and 0.21, so 4024.1. So equals 4024 of air, not just O2, but total air, which is nitrogen plus O2. Alrighty, so there we have it, and hopefully this clears things up. And we did this one the so-called short way. We didn't convert to moles this time, and but you could do it either way if you want. Anywho, if you have any questions, feel free to ask. Okay, not to get away from our process flowchart, here's what the process flowchart for that problem would look like. We have some natural gas coming in with the natural gas conditions. We have some air coming in. We know the composition of air. It's 79% 79% N2, 21% O2, and we have the pressure and temperature conditions. And sometimes you use excess air, okay, to make sure the reaction happens. So on the output, you'll also get some O2. If you're not using excess air, you assume that all the oxygen went to making CO2 and O2. and some kind of other things. Okay, so you see like tie components. So carbon is a tie component. So if you see carbon on one side and carbon on the other side, it's a tie component. Okay, hydrogen also, but it has a different form when it comes out. It's made friends with something else. Here we have pure N2 and pure O2 because of the excess air. So for this first lecture on combustion reactions, we've dealt with just simple reactions. We're going to do some more complex, or at least a couple of examples of more complex combustion reactions in the next lecture. So please go back and even watch this one again to be sure you have the basics down, and then we'll move on to the next lecture. If you have any questions, always feel free to ask me or the TA, and have fun with this. This is kind of cool stuff, and fire, right? So anyway, thank you for your time, and good luck with these problems.
Oh my. It's the end of the lecture. If you have any questions, you can email me at drobertson@utep.edu.